The morning of March 17, 1945. Skies above Kagoshima Bay, southern Kyushu. Lieutenant Commander Minoru Genda stood on the observation deck at Kanoya Air Base, his binoculars trained on a formation of American fighters approaching from the southeast. The distinctive inverted gull wings were unmistakable. Corsairs, 20, perhaps 30 of them, their Pratt and Whitney engines producing that peculiar whistling sound that had given them their Japanese nickname. What happened in the next 90 seconds would fundamentally alter Genda's understanding of what his pilots faced. The lead Corsair, pursued by a Zero that had managed to gain a firing position, suddenly pitched upward into a climb so steep it seemed to violate the laws of physics. Not a gradual zoom, not the curving arc Japanese fighters executed when trading speed for altitude, but an almost vertical ascent that looked more like a rocket launch than an aircraft maneuver. Genda checked his watch, timing the climb. 3,000 feet in 60 seconds, then 4,000. The Zero, attempting to follow, fell away after 1,500 feet, its engine screaming in protest, its airframe shuddering at the edge of a stall. The Corsair continued upward, seemingly unburdened by gravity, until it rolled inverted at 6,000 feet and dove back onto the Zero that had been chasing it moments before. Genda lowered his binoculars and spoke a single word that would appear in his after-action report later that day: impossible. But it was not impossible. It was simply American engineering applied with devastating effectiveness to the problem of air superiority. And for Japanese pilots who had spent 3 years mastering the delicate art of energy management in lightweight fighters, the Corsair's ability to climb vertically at 3,000 feet per minute represented something far worse than superior technology. It represented the end of any remaining advantage they possessed. The story of how Japanese pilots came to utter the word impossible when watching Corsairs climb is not merely a tale of engineering specifications. It is the chronicle of a psychological transformation, the moment when Japan's aviation community confronted the full magnitude of what they faced. Through examination of this single capability, climb rate, they would discover truths about engine technology, propeller design, and power-to-weight ratios that revealed the unbridgeable gap separating Japanese and American aviation by 1945. If you're enjoying this deep dive into the story, hit the subscribe button and let us know in the comments from where in the world you are watching from today. The Corsair's extraordinary climb performance did not emerge by accident. It was the deliberate result of design decisions made 7 years earlier, when Chance Vought engineers confronted the Navy's demand for a fighter capable of exceeding 400 miles per hour. To achieve this, Chief Designer Rex Beisel made a choice that would define every aspect of the Corsair's character. He would build the aircraft around the largest, most powerful engine available, accepting whatever design challenges that decision created. The Pratt and Whitney R-2800 double Wasp represented American aero engine development at its peak. 18 cylinders arranged in 2 rows of 9, displacing 2,800 cubic inches and producing over 2,000 horsepower in standard configuration. With water injection, available on later variants, power output could reach 2,450 horsepower for short bursts. This was not merely more powerful than Japanese engines. It was power on a scale Japanese manufacturing could not replicate. To extract maximum performance from this massive engine, Vought engineers designed a propeller system unlike anything on Japanese fighters. The Hamilton Standard hydromatic propeller measured 13 feet 4 inches in diameter, the largest ever fitted to a single-engine fighter. Variable pitch capability allowed the propeller to optimize efficiency across the entire flight envelope, from takeoff through combat maneuvers to high-altitude cruise. The engineering challenge was immediate: how to provide ground clearance for such a massive propeller while maintaining structural efficiency for carrier operations. The solution became the Corsair's most distinctive feature. Rather than using conventional straight wings, Beisel's team created an inverted gull wing design. The wings angled downward from the fuselage before leveling out, creating a distinctive M shape when viewed from the front. This configuration allowed relatively short landing gear, while providing propeller clearance. The anhedral angle where the wing met the fuselage also created optimal aerodynamic conditions, minimizing drag. The bent wing was heavier and more difficult to construct than conventional designs, offsetting these benefits partially, but it solved the ground clearance problem while enabling Vought to extract every possible advantage from the massive engine and propeller combination. The prototype F4U flew on May 29, 1940, piloted by Lyman Bullard Jr., Vaught's chief test pilot, from the factory airfield in Stratford, Connecticut. On October 1, 1940, during a test flight between Stratford and Hartford, the F4U achieved a ground speed of 405 miles per hour with tailwind assistance, making headlines as the first single-engine American fighter to reach this milestone. The aircraft's actual maximum level flight speed was 378 miles per hour at 23,500 feet. Still exceptional performance for 1940, but what truly distinguished the Corsair was not top speed. It was the ability to reach that speed rapidly through vertical or near-vertical climbs that Japanese fighters simply could not match. Production F4U Corsairs began reaching operational units in late 1942. Marine Fighter Squadron 124, VMF 124, received the first combat-ready aircraft, deploying to Henderson Field, Guadalcanal, on February 12, 1943. The Corsairs' combat debut proved inauspicious. On February 14, 1943, during what became known as the St. Valentine's Day Massacre, Corsairs suffered a disastrous first engagement. 9 American aircraft were lost, including 2 Corsairs, multiple P-38 Lightnings, P-40 Warhawks, and bombers, while Japanese defenders lost only a single Zero fighter. The 9-to-1 loss ratio in Japan's favor was so severe that daylight bombing missions to Bougainville were suspended pending tactical reassessment. This engagement demonstrated that superior technology alone could not guarantee victory. Tactics, experience, and proper deployment mattered equally. American pilots adapted quickly. They learned that the Corsairs' strengths lay not in dogfighting, but in what became known as boom and zoom tactics. The Corsair could not outturn a Zero in slow-speed maneuvering, but it could outdive, outclimb, and outrun any Japanese fighter. Proper tactics meant maintaining speed and altitude advantage, diving on enemy aircraft, firing, and using superior speed and climb rate to disengage before the enemy could respond. Second Lieutenant Kenneth A. Walsh of VMF 124 became the first Corsair ace on May 13, 1943, mastering these tactics and eventually achieving 21 victories. Walsh later stated his tactical philosophy clearly: "I learned quickly that altitude was paramount. Whoever had altitude dictated the terms of the battle, and there was nothing a Zero pilot could do to change that. We had him. The F4U could outperform a Zero in every aspect except slow speed maneuverability and slow speed rate of climb." The critical phrase was slow speed rate of climb. At speeds below 200 knots, the Zero's lightweight and large wing area gave it competitive climb performance. But the moment combat speeds increased above 230 miles per hour, the Corsair's advantages became overwhelming. Its massive engine and efficient propeller converted horsepower into altitude with ruthless efficiency. As the war progressed through 1943 and 1944, the Corsair's reputation grew. Marine squadrons in the Solomon Islands, flying from hastily constructed Coral Airstrip, exploited the aircraft's ruggedness and climb performance to devastating effect. The Corsair proved capable of absorbing battle damage that would have destroyed lighter Japanese fighters. Its 650 caliber Browning machine guns, the 4 inboard guns carrying 400 rounds each, and the 2 outboard guns carrying 375 rounds each, totaling 2,350 rounds, provided overwhelming firepower. Later variants, like the F4U-1C, replaced the machine guns with 4 20mm cannons, though many pilots preferred the reliability and ammunition capacity of the 50 caliber weapons. The Corsair's versatility extended beyond air combat. By mid-1944, Corsairs regularly carried external ordnance, 1,000-pound bombs on centerline and wing racks, 8 5-inch high-velocity aircraft rockets, or napalm canisters. This fighter-bomber capability made the Corsair invaluable for close air support during amphibious operations. What Japanese pilots encountered in combat told only part of the Corsairs' story. From the cockpit of a Zero or other Japanese fighter, a pilot saw an opponent that was faster, stronger, more resilient, and crucially, capable of climbing at rates that seemed to defy physics. Understanding the engineering behind these advantages required direct observation and technical analysis. Japan's capability for technical intelligence centered on facilities like the Yokosuka Naval Air Technical Arsenal south of Tokyo and the Army Aviation Technical Research Institute at Tachikawa. These organizations had been examining captured Allied aircraft throughout the war, recovering examples from battlefields across the Pacific. By 1945, they had accumulated considerable data on American fighters, including detailed observations of Corsair performance in combat. But observation from the ground or from the cockpit of an opposing fighter provided limited insight. What Japanese aviation specialists needed was opportunity to measure, to calculate, to understand precisely how the Corsair achieved its extraordinary climb performance. That opportunity came in early 1945, when salvage crews recovered a Corsair that had ditched after engine failure during combat operations off Japan's coast. The aircraft had suffered water damage during its forced landing, but the basic structure remained sound. Recovery teams worked to prevent complete sinking, and the fighter was transported to facilities for examination. Initial assessment focused on overall condition. Despite saltwater immersion, much of the Corsair remained intact. The massive Pratt Whitney engine would require complete disassembly and cleaning, but the airframe structure showed no combat damage. Japanese specialists began with systematic photography and measurement. Every dimension was recorded. Wingspan of 40 feet 11.7 inches, length of 33 feet 4 inches, height of 15 feet with wings extended or 16 feet 2.3 inches when wings were folded for carrier storage. The inverted gull wing configuration immediately drew attention. Japanese designers understood the aerodynamic and structural advantages of this design, but they also recognized its manufacturing complexity. The examination revealed something that particularly surprised the technical team. Despite the Corsair's advanced nature, portions of its outer wing surfaces were covered with fabric rather than metal, aft of the main wing spar and armament bays. Both upper and lower surfaces used fabric covering, as did the control surfaces, ailerons, elevators, and rudder. Japanese aviation specialists initially found this puzzling. By 1944 to 1945, most modern fighters used all-metal construction. Further analysis revealed sophisticated reality. The fabric covering was a deliberate design choice from the aircraft's 1938 to 1940 development period. It reduced weight where structural loads were minimal, saving aluminum for critical load-bearing components. The fabric was specially treated material that, when properly applied, provided adequate strength and weatherproofing while weighing significantly less than metal skinning. This represented mature understanding of resource allocation for optimal performance. Disassembly of the wing structure revealed construction methods that technical personnel found both impressive and troubling. The main wing spar, the critical structural element carrying flight loads, was a massive forging of exceptional quality. American metallurgy had produced aluminum alloy forgings with strength characteristics Japanese facilities struggled to match. The spar's dimensions and load-bearing capacity exceeded anything in comparable Japanese fighters. This single component illustrated a fundamental difference. American industry could produce large, complex forgings with consistent quality, while Japanese manufacturers increasingly relied on built-up structures assembled from smaller components. The wing's internal structure demonstrated similar sophistication. Ribs stamped from aluminum sheet showed remarkable precision and consistency. Each rib was virtually identical to the next, indicating manufacturing processes with tight quality control. Japanese aircraft production increasingly struggled with consistency as the war progressed, with individual aircraft showing variations in component quality. Attention turned to the Corsair's armament installation. 6 Browning AN/M2 50 caliber machine guns mounted in the wings represented formidable firepower. The installation was compact, reliable, and designed for easy maintenance. What struck Japanese examiners was not just the firepower, but the system's completeness. Ammunition boxes, feed systems, spent cartridge ejection, and charging mechanisms were all engineered to work seamlessly together. The guns themselves were specimens of precision manufacturing. American ordnance production had achieved reliability levels Japanese industry envied. The Browning M2 machine gun was a mature design, perfected through decades of development and manufactured by the millions with extraordinary consistency. Japanese technicians examining these weapons recognized manufacturing techniques and quality standards their own factories could not consistently achieve. The discovery of 150 pounds of armor plate protecting the cockpit and a 1.5-inch thick bulletproof glass panel behind the windscreen reinforced impressions of American design. Philosophy. Japanese fighters had largely abandoned heavy armor protection in favor of lighter weight and better maneuverability. The Zero's early success seemed to validate this approach, but as American fighters grew more powerful and better armed, the lack of protection became fatal. The Corsair demonstrated that proper engineering could incorporate substantial protective armor without sacrificing performance, made possible by the massive power of the R-2800 engine. That engine dominated the technical examination. The Pratt Whitney R-2800 double wasp represented American aero engine development at its peak. 18 cylinders arranged in 2 rows of 9, displacing 2,800 cubic inches and producing over 2,000 horsepower. This engine was a masterpiece of mechanical engineering. Japanese engineers had encountered this engine before in captured aircraft, but never had they possessed an example in relatively good condition for thorough analysis. The engine's construction revealed manufacturing capabilities that seemed almost incomprehensible. Cylinders were precisely machined with tolerances measured in thousandths of an inch. Pistons, connecting rods, and crankshaft components showed surface finishes and dimensional accuracy that Japanese engine manufacturers struggled to achieve. The two-stage supercharger system, designed to maintain power at high altitudes, incorporated complex internal passages and precisely fitted rotating components. Japanese attempts to develop comparable supercharger systems had largely failed due to manufacturing limitations. Perhaps most impressive was the engine's reliability and power output. American radial engines routinely produced their rated horsepower for hundreds of hours between overhauls. Japanese engines, even new examples, often failed to achieve their theoretical power ratings and required frequent maintenance. The R-2800's consistent performance came from superior metallurgy, better lubricants, more precise manufacturing, and more sophisticated quality control. But it was the propeller system that proved most revealing about the Corsair's climb performance. The Hamilton Standard hydromatic propeller, with its 13 feet 4-inch diameter and variable pitch capability, represented advanced aerodynamic design and hydraulic control systems. Japanese engineers understood propeller theory, but lacked manufacturing facilities capable of producing large propellers with necessary precision. More critically, they understood that this propeller system was the key to converting the engine's massive horsepower into vertical climb rate. The technical analysis revealed the fundamental mathematics of climb performance. Rate of climb depended on excess power, the difference between power available from the engine and power required to maintain level flight. The Corsair's 2,000 horsepower engine, combined with its efficient propeller and relatively clean aerodynamics, generated enormous excess power throughout its flight envelope. This excess power translated directly into vertical velocity. Japanese engineers calculated the numbers and confronted uncomfortable reality. The early F4U variant achieved climb rates of approximately 2,890 feet per minute at sea level. The F4U, with its more powerful R-2800 18W engine, producing 2,100 horsepower, or 2,450 horsepower with water injection, achieved climb rates exceeding 4,360 feet per minute. The F4U, with its two-stage supercharger and 2,760 horsepower, reached 4,840 feet per minute at sea level. These were not estimates or propaganda figures. They were verified performance data that Japanese technical intelligence confirmed through examination of captured aircraft and analysis of combat observations. By comparison, the Mitsubishi A6M20, Japan's primary fighter throughout most of the war, achieved a maximum climb rate of approximately 3,090 feet per minute at sea level when flown by Japanese pilots using military power settings. The A6M3 and A6M5 variants achieved similar rates. On paper, this seemed competitive with the early Corsair variants, but the comparison was deceptive. The Zero achieved its climb rate at lightweight, approximately 5,300 pounds fully loaded, and only at relatively slow speeds where its large wing area provided maximum efficiency. Above 230 miles per hour, the Zero's climb rate deteriorated rapidly as drag increased, and its engine struggled to maintain power. The Zero's 950 horsepower Nakajima Sakai radial engine simply could not compete with the Corsair's power output. More critically, the Zero could not maintain its climb rate while maneuvering aggressively. Any turning or rolling motion at high angles of attack caused the Zero to bleed energy rapidly. The lightweight fighter's lack of excess power meant that once energy was lost, it could not be quickly regained. Japanese pilots learned to husband their energy carefully, knowing that a single mistake could leave them vulnerable. The Corsair, by contrast, could maneuver aggressively and still maintain high climb rates. Its massive power reserve meant that energy lost in a turn could be recovered quickly through a brief climb. American pilots exploited this ruthlessly, using vertical maneuvers that Japanese fighters simply could not follow. The tactic became so common that Japanese pilots developed a term for it, the vertical escape, performed by Corsairs that refused to engage in horizontal turning fights. Combat reports from Japanese fighter units in 1944 and 1945 repeatedly described the same tactical sequence. American fighters, usually Corsairs or Hellcats, would approach at high speed and altitude. Japanese fighters would attempt to intercept, using their superior low-speed maneuverability to gain firing positions. The American aircraft would accelerate away in a shallow dive, building speed to over 300 miles per hour. Then, at the moment Japanese fighters committed to pursuit, the American aircraft would pitch upward into a nearly vertical climb. Japanese pilots would attempt to follow, pulling their control sticks back, pointing their aircraft skyward. For perhaps 5 or 10 seconds, the Japanese fighters would climb, their engines roaring, their airframes shuddering at the edge of a stall. Then the climb would end, speed would bleed away, the nose, it would drop, the aircraft would fall away into a stall or spin. Meanwhile, the Corsair would continue climbing, seemingly unburdened by the constraints of physics. 1,000 feet vertical separation, 2,000 feet, 3,000 feet. The Corsair would roll inverted at the top of its climb, now holding both altitude and speed advantage, and dive back onto the Japanese fighters that had been pursuing it moments before. The psychological impact of this capability cannot be overstated. Japanese pilots, trained in the precision art of energy management, understood that vertical climbs were dangerous. They bled speed rapidly, leaving aircraft vulnerable if the climb did not result in a successful attack. Japanese fighters performed zoom climbs, trading speed for altitude in carefully calculated arcs that maintained enough airspeed to avoid stalling. The idea of pointing an aircraft straight up and simply climbing, relying on raw engine power to overcome gravity, seemed reckless. Until they watched Corsairs do it repeatedly, with impunity. Lieutenant Commander Minoru Genda's observation deck encounter was not unique. Similar reports came from fighter units across the Pacific in 1945. From the Philippines, where Japanese pilots described Corsairs climbing vertically after bombing runs on Japanese positions. From Okinawa, where Corsairs performing combat air patrol would zoom to intercept altitude whenever Japanese aircraft appeared. From the home islands, where B-29 escort fighters demonstrated climb capabilities that seemed impossible. The word impossible appeared with striking frequency in Japanese after-action reports, not as hyperbole, but as the only word that seemed adequate to describe what pilots were witnessing. The Corsairs' climb performance violated every assumption about fighter aircraft that Japanese aviation doctrine had built over years of combat experience. It suggested that American engineering had solved problems Japanese designers did not know could be solved. The examination of the captured Corsair at Yokosuka Naval Air Technical Arsenal occurred as Japan faced imminent defeat. American B-29 bombers were systematically destroying Japanese cities. The Navy had been shattered at Leyte Gulf. The Philippines had been liberated. Iwo Jima had fallen, and Okinawa was under assault. In this desperate context, the Corsair examination took on somber significance. It was not intelligence gathering for future victories, but a final reckoning with technological reality. Japanese engineers at Yokosuka and Tachikawa wrote technical reports documenting their findings. These reports detailed measurements, described manufacturing techniques, and offered assessments of American capabilities. The tone was professional, but could not hide underlying implications. In nearly every category examined, American technology exceeded Japanese capabilities. The gap was not small or easily closed. It represented years of industrial development, massive investments in research and tooling, sophisticated supply chains, and resources Japan simply did not possess. The climb rate disparity crystallized all of these differences into a single, measurable performance metric. Japanese engineers could calculate the precise power-to-weight ratios. They could measure the propeller efficiency. They could analyze the supercharger design. And from these calculations, they could determine exactly how far behind Japanese aviation had fallen. The mathematics were unforgiving. The Corsair's power-to-weight ratio, approximately 6 pounds per horsepower for later variants, compared favorably to the Zero's 5.6 pounds per horsepower. But this comparison was misleading. The Corsair achieved its ratio while carrying armor protection, self-sealing fuel tanks, substantially more ammunition, and far more robust structure. The Zero achieved its ratio through weight reduction that compromised survivability. More importantly, the Corsair's power-to-weight ratio remained favorable across a much wider speed range. The Zero's advantage existed primarily at low speeds, where its large wing area minimized induced drag. At combat speeds above 250 miles per hour, the Corsair's cleaner aerodynamics and vastly superior power output gave it overwhelming advantage in any maneuver, requiring energy, particularly vertical climbs. Japanese pilots who survived encounters with Corsairs and returned to base provided consistent testimony about the aircraft's capabilities. They described the distinctive whistling sound the inverted gull wings produced during high-speed dives, giving rise to the Corsair's Japanese nickname, Whistling Death. They described the aircraft's seemingly unlimited ammunition capacity, allowing sustained firing that would have exhausted a Zero's cannon ammunition in seconds. Most consistently, they described the vertical climbs. Pilots used phrases like standing on its tail, climbing like a rocket, and going straight up. These descriptions appeared in combat reports, intelligence summaries, and post-war interviews. The language was remarkably consistent across different units, different time periods, and different combat theaters. The Corsair's climb performance had made such an impression that it became the defining characteristic Japanese pilots associated with the aircraft. Technical analysis revealed why the F4U variant, which became the most common Corsair in the final year of the war, could accelerate from cruise speed to maximum speed while simultaneously climbing at over 3,000 feet per minute. This combination, speed increase plus vertical velocity, was something Japanese fighters simply could not match. The Zero could climb quickly at slow speeds, or it could accelerate in level flight, but it could not do both simultaneously without its engine struggling. The Corsair's two-stage supercharger, particularly on the F4U variant, maintained sea-level power output up to approximately 16,000 feet. This meant the aircraft could sustain maximum climb rate through the altitude band where most Pacific air combat occurred, between 10,000 and 25,000 feet. Japanese fighters, with their single-stage superchargers or less sophisticated boost systems, experienced significant power loss above 15,000 feet. Combat at altitude increasingly favored American aircraft. The examination also revealed the Corsair's operational flexibility. The aircraft could carry a 160-gallon drop tank on the centerline, extending range to over 1,000 miles. With this configuration, The Corsair could fly combat air patrol for hours, climb to intercept altitude when threats appeared, engage in combat, and still have fuel to return to base. This endurance, combined with climb performance, made the Corsair ideal for defending carrier task forces against Japanese attack aircraft. During the Okinawa campaign in 1945, Corsairs performed this mission with devastating effectiveness. Japanese special attack aircraft, kamikazes, attempted to overwhelm American defenses through sheer numbers. But Corsairs on combat air patrol could intercept these attacks at maximum efficiency. Radar would detect incoming Japanese aircraft at ranges exceeding 50 miles. Corsairs would be vectored toward the threat. Using their superior speed, they would close the distance rapidly. Then, from positions below or to the side of Japanese formations, Corsairs would execute zoom climbs, ascending to attack altitude in seconds. The Japanese aircraft, typically bomb-laden fighters or modified bombers, had no defense against these tactics. They were too slow to evade, too heavily loaded to maneuver, and too lightly armed to fight back effectively. Corsair pilots would make high-speed passes, using their 650 caliber machine guns to devastating effect, then zoom back to at altitude to repeat the attack. If you find this story engaging, please take a moment to subscribe and enable notifications. It helps us continue producing in-depth content like this. The statistics from Okinawa tell the story. Marine Corsair squadrons were credited with 506 of the approximately 3,000 Japanese aircraft expended during the battle. Roughly half were kamikazes. Navy fighters and anti-aircraft fire accounted for most of the rest. Less than 10% of kamikaze aircraft managed to mount attacks on American ships. The Corsairs' ability to climb rapidly to intercept altitude was crucial to this defensive success. Japanese aviation commanders recognized what was happening. Intelligence summaries from 1945 described American fighters, particularly Corsairs, as possessing superior high-speed performance and vertical climbing ability. Tactical directives instructed Japanese pilots to avoid vertical maneuvers when engaged by American fighters. Avoid prolonged combat, one directive stated. Use clouds and terrain to break contact. Do not attempt to outclimb enemy fighters. These were not the directives of a confident air force. They were the instructions of commanders who understood their pilots faced overwhelming technological disadvantage. The best tactic available was simply to survive, to avoid combat when possible, to strike only when circumstances provided advantage. The idea of seeking out and defeating American fighters in air-to-air combat had become unthinkable by 1945. The psychological dimension of this technological gap extended beyond individual pilots. Japanese aviation industry leaders understood that domestic engine development had failed to keep pace with American advances. The most powerful Japanese engine in widespread production by 1945 was the Mitsubishi Mk9, a Kinsei radial, producing approximately 1,500 horsepower. This represented significant improvement over the 950 horsepower engines powering most Japanese fighters, but it still fell far short of American capabilities. Japanese engineers had designed more powerful engines. The Nakajima NK9H Homare radial was rated at over 1,800 horsepower. The Mitsubishi Ha-43 radial could produce over 2,000 horsepower, but these engines suffered from reliability problems, manufacturing difficulties, and insufficient development time. They were installed in small numbers of aircraft, primarily experimental or limited production variants, but never achieved the reliability needed for frontline service. The fundamental problem was manufacturing precision. American engines achieved their power output through precise tolerances, high-quality metallurgy, and sophisticated machining. Japanese manufacturing facilities, operating under increasingly difficult conditions by 1945, could not consistently achieve these standards. Engines that performed adequately in testing often failed in service. Quality control, never matching American standards, deteriorated further as the war progressed. The Corsair examination revealed these gaps with painful clarity. Japanese engineers examining the R-2800 engine could see exactly what American manufacturing could achieve. They could measure the tolerances, analyze the materials, and understand the design sophistication. What they could not do was replicate it. Japan's industrial infrastructure, strained by years of war, could not suddenly produce facilities capable of matching American capabilities. This realization extended beyond engines to every aspect of fighter design. The Corsairs propeller required precision manufacturing Japanese facilities struggled to provide. Its hydraulic systems demanded quality control Japanese suppliers could not guarantee. Its electrical systems needed components Japanese industry produced in limited quantities. Even basic materials, the aluminum alloys forming the airframe structure, exceeded Japanese metallurgical capabilities in some respects. The captured Corsair thus became more than intelligence about a specific aircraft. It became a comprehensive illustration of the industrial and technological gap separating Japan from America. Every system, every component, every design choice reflected resources, capabilities, and manufacturing sophistication that Japan could not match. For Japanese engineers examining the aircraft, this recognition must have been profoundly disheartening. By war's end in August 1945, Japanese aviation had been effectively destroyed. Thousands of aircraft had been lost in combat. Thousands more had been expended in kamikaze attacks. Pilot training programs had collapsed as fuel shortages made flying hours impossible to accumulate. Experienced pilots were dead. The survivors lacked fuel, lacked spare parts, and increasingly lacked aircraft. When American occupation forces arrived in Japan in September 1945, they found airfields littered with wrecked aircraft. Some had been destroyed by American bombing. Others had been deliberately sabotaged by their own crews to prevent capture. Still others sat abandoned, out of fuel and parts, monuments to a defeated air force. The Corsair, meanwhile, continued its operational career long after World War II ended. The aircraft fought in the Korean War from 1950 to 1953, where it proved effective in ground attack and close air support roles, even as jet fighters took over air superiority missions. On August 7, 1952, Marine Captain Jesse Folmar, flying an F4U Corsair, shot down a Soviet-built MiG-15 jet fighter, one of the few propeller-driven aircraft to achieve an air-to-air victory against a jet in combat. The encounter demonstrated that the Corsair's raw power and climb performance remained relevant even in the jet age. Folmar used boom and zoom tactics, identical to those developed against Japanese fighters in World War II, diving from altitude to build speed, firing a burst, then using the Corsair's climb rate to regain altitude before the faster jet could respond. The tactic worked because the Corsair could still outclimb many first-generation jets at low to medium altitudes. Foreign air forces, including France, flew Corsairs in colonial conflicts through the 1960s. The last combat missions by Corsairs occurred in July 1969 during the brief soccer war between Honduras and El Salvador. On July 17, 1969, Honduran Captain Fernando Soto, flying an F4U-5, shot down 3 Salvadoran aircraft, including 2 FG-1D Corsairs, the final combat victories for the type, ironically achieved against other Corsairs. From its first flight in 1940 to its final combat missions nearly 30 years later, the Corsair proved one of aviation history's most successful and long-lived fighter designs. Its climb performance, the characteristic that so impressed and dismayed Japanese pilots, remained competitive throughout its operational life. The combination of powerful engine, efficient propeller, and clean aerodynamics created a performance envelope that few aircraft of its era could match. For Japan, the encounter with the Corsair was part of a larger reckoning with technological reality during the American occupation. Japanese engineers and scientists who had struggled against material shortages and industrial limitations during the war now worked with American occupation authorities to rebuild Japanese industry. Lessons learned from examining American technology, including the Corsair, influenced post-war Japanese manufacturing philosophy. The emphasis on quality, precision manufacturing, and continuous improvement that characterizes modern Japanese industry has roots in the hard lessons learned when Japanese engineers examined what American industry could produce. The transformation was neither quick nor easy. Post-war Japan began with shattered industrial infrastructure and limited resources, but Japanese engineers possessed technical knowledge and understanding of modern manufacturing principles. They had studied American methods, examined American products, and understood what excellence required. The rebuilding of Japanese aviation industry took decades. Mitsubishi, which had produced the Zero fighter, transitioned to licensed production of American aircraft designs before eventually developing indigenous designs. Japan's aerospace industry in the 1950s and 60s produced aircraft under license from American manufacturers, learning manufacturing techniques and quality control methods. By the 1970s and 80s, Japanese aerospace companies contributed components to international programs, applying the precision manufacturing capabilities they had developed. The Corsair itself influenced Japanese thinking about fighter design in subtle ways. Post-war Japanese aerospace engineers, when developing indigenous aircraft, emphasized reliable engines, robust structure, and performance margins. The lightweight, fragile design philosophy that characterized the Zero gave way to approaches prioritizing survivability and sustained performance. This shift reflected lessons learned through bitter experience about what modern air combat required. The specific Corsairs captured by Japanese forces during the war have vanished. Most were likely destroyed in the chaotic final months of the war or scrapped during the immediate post-war period. American occupation forces collected Japanese technical intelligence materials, including reports on captured Allied aircraft, recognizing their historical value. These documents now rest in archives, providing insight into what Japanese engineers learned from examining American technology. The technical reports on the Corsair, written by Japanese engineers in 1945, make for sobering reading. The language is professional and analytical, but underlying themes emerge clearly. American manufacturing precision exceeded Japanese capabilities. American engines produced power outputs. Japanese designs could not match reliably. American aircraft combined characteristics, high speed, heavy armament, armor protection, that Japanese fighters sacrificed in pursuit of maneuverability. Most tellingly, the reports acknowledge that closing the technological gap would require not just better designs, but fundamental improvements in manufacturing capabilities, materials, science, and industrial infrastructure. These were not problems that could be solved quickly or easily. They required investment, time, and resources that Japan did not possess in 1945. The war would end before any of these improvements could be implemented. The story of Japanese pilots saying impossible when watching Corsairs climb at 3,000 feet per minute represents more than amazement at a specific aircraft's performance. It represents the moment when Japan's aviation community fully grasped the magnitude of the challenge they faced. The Corsair's climb rate was not achieved through some exotic technology or secret design. It was the product of superior engineering, better manufacturing, more powerful engines, and the industrial capacity to produce these aircraft in quantity. Japan had faced American industrial might before. The quantitative advantage, the sheer number of aircraft, ships, and weapons American factories produced, was recognized early in the war. But the qualitative advantage, the superior performance of American equipment, took longer to fully appreciate. Early war combat had shown that Japanese aircraft could compete effectively when flown by skilled pilots using proper tactics. By 1945, even skilled pilots using optimal tactics faced overwhelming disadvantage. The Corsair exemplified this transformation. Its ability to climb vertically at rates Japanese fighters could not match eliminated the tactical flexibility Japanese pilots relied upon. Unable to escape through vertical maneuvers, unable to maintain energy in prolonged combat, unable to match American aircraft in speed or firepower, Japanese pilots faced impossible odds. The word impossible, used by Lieutenant Commander Genda and countless other Japanese observers, was not hyperbole. It was accurate assessment of the tactical reality they confronted. American pilots flying Corsairs understood and exploited these advantages ruthlessly. Combat reports from 1944 and 1945 describe tactics built around the aircraft's climb performance. Standard procedure when jumped by Japanese fighters was to accelerate in a shallow dive, building speed to over 300 miles per hour, then execute a zoom climb to regain altitude advantage. The Japanese fighters, unable to follow, would be left below and behind, vulnerable to follow-up attacks. Marine and Navy fighter squadrons developed variations on this basic tactic. Some pilots would climb to extreme altitude before combat, 30,000 feet or higher, then dive on Japanese formations from above, using the speed gained in the dive to zoom back to altitude after their attack runs. Others would orbit at medium altitude, waiting for Japanese aircraft to approach, then use the Corsairs' superior climb rate to position themselves above the enemy before engaging. The flexibility these tactics provided cannot be overstated. American pilots could choose when to fight, could dictate engagement terms, and could disengage at will. Japanese pilots had no counter. They could not force combat on unwilling opponents. They could not prevent American aircraft from escaping through vertical maneuvers. They could not maintain energy equality with aircraft possessing far superior power-to-weight ratios. The Corsairs' climb performance, combined with its speed and firepower, created a tactical environment where Japanese pilots were simply outmatched. This tactical dominance contributed to the Corsairs' extraordinary combat record. The aircraft achieved an official kill ratio of 11-1 against Japanese aircraft. American pilots flying Corsairs shot down 2,140 Japanese aircraft, while losing only 189 Corsairs to enemy action during World War II. These numbers reflected not just the Corsairs' technological superiority, but the entire American war machine's advantages: better training, superior logistics, overwhelming production capacity, and advanced technology at every level. The 11-1 kill ratio represented multiple factors. The Corsairs' performance advantages certainly contributed, but equally important were pilot quality, tactical doctrine, radar-guided interceptions, and numerical superiority. By 1945, American fighter pilots averaged hundreds of training flight hours before entering combat. Japanese pilots, due to fuel shortages and collapsed training programs, entered combat with perhaps 50 to 100 hours of flight time, sometimes less. The combination of superior aircraft and superior pilot training created insurmountable odds. A well-trained American pilot flying a Corsair against an inexperienced Japanese pilot in a Zero was not a fair fight. It was a systematic execution. The Corsairs' climb performance ensured that even if the Japanese pilot had superior tactical position initially, the American pilot could escape, reset the engagement, and attack from advantage. There was no scenario where the Japanese pilot held lasting advantage. Japanese aviation commanders understood this reality by 1945. Tactical directives increasingly emphasized survival over victory. Avoid combat with American fighters became standard guidance. Strike ground targets when fighter opposition is absent. Use weather and terrain to break contact. These were the tactics of an air force that had lost air superiority and knew it could not be regained. The Corsair, with its ability to climb at 3,000 feet per minute or more, exemplified why regaining air superiority was impossible. The contrast with early war combat could not be more stark. In 1942, Japanese pilots in Zero fighters dominated Pacific skies. American pilots fled from Zeros when possible, fought defensively when forced to engage, and suffered catastrophic losses. The kill ratios favored Japan heavily. Japanese pilots, many of them veterans with years of combat experience, flew aircraft optimized for the maneuvering combat that characterized early air battles. By 1945, the situation had completely reversed. American pilots in Corsairs and Hellcats hunted Japanese aircraft with impunity. Japanese pilots avoided combat when possible, fled when engaged, and survived primarily through luck rather than skill. The kill ratios favored America overwhelmingly. The transformation took only 3 years, from early 1942 to mid-1945, but it represented fundamental shifts in aircraft design, pilot training, tactical doctrine, and industrial capacity. The Corsairs' climb performance was one factor among many in this transformation, but it was a highly visible factor, one that Japanese pilots could directly observe and experience. Watching a Corsair climb vertically at 3,000 feet per minute, continuing upward while Japanese fighters fell away into stalls, provided visceral illustration of the technological gap. It was a gap measured not in abstract statistics, but in feet per minute, in altitude gained, in tactical options available to the enemy and denied to Japanese pilots. Lieutenant Commander Minoru Genda, who observed Corsairs climbing impossibly on that March morning in 1945, survived the war. He later served in the post-war Japanese self-defense forces, eventually achieving the rank of general. In post-war interviews, he spoke about the challenges Japanese aviation faced in the final years of the conflict. He mentioned the Corsair specifically, describing it as one of the most capable American fighters, particularly in vertical maneuvers. Genda's assessment, delivered with the benefit of hindsight and without wartime propaganda constraints, acknowledged what Japanese pilots had known but could not always say publicly during the war. American fighters, particularly late-war variants like the Corsair and Hellcat, were simply superior aircraft. They were faster, better armed, better protected, and crucially, capable of vertical performance Japanese fighters could not match. The climb rate advantage was one part of this superiority, but it was the part that Japanese pilots found most psychologically demoralizing. Being outgunned was frustrating but understandable. Being slower was disappointing but manageable through tactical adaptation. But being unable to climb, unable to escape vertically, unable to use the third dimension effectively, eliminated the last tactical options Japanese pilots possessed. It reduced combat to brutal simplicity. American aircraft could engage or disengage at will. Japanese aircraft had to accept whatever engagement terms the Americans dictated. This was not combat between equals. It was systematic domination. The examination of captured Corsairs provided Japanese engineers with detailed understanding of how this performance was achieved. The reports documented the engine specifications, propeller design, supercharger configuration, and power output. Japanese engineers could calculate exactly how much power was required to achieve 3,000 feet per minute climb rates. They could analyze the propeller efficiency and understand how Hamilton Standard had optimized the design. They could study the supercharger system and recognize the sophisticated engineering behind maintaining power output across wide altitude ranges. What they could not do was replicate any of it. The knowledge gained from examining captured Corsairs came too late to influence Japanese aircraft development meaningfully. The war would end before any of these lessons could be applied to new designs. Even if time had been available, Japan's industrial capacity could not have produced the engines, propellers, and manufacturing precision required. The technological gap was not something that could be closed through better designs alone. It required infrastructure, investment, and resources Japan simply did not possess. The Corsair examination thus became an epitaph for Japanese aviation. It documented, with engineering precision, exactly how far Japan had fallen behind. Every measurement, every specification, every analysis confirmed what combat losses had already proven. Japan could not compete with American aviation technology in 1945. The gap was too wide, the resource disparity too great, the manufacturing capability difference too fundamental. Understanding the problem did not provide solutions when solutions required rebuilding entire industries under wartime conditions while under sustained enemy attack. Thank you for watching. For more detailed historical breakdowns, check out the other videos on your screen now, and don't forget to subscribe.